So we saw that a weak acid is one which, when you put it in water, will partially react with the water molecules to give you H3O+. And similarly, a weak base is one that when you put it in water will partially react with the water molecules to give you hydroxide ions, right? They don't completely react in the way that a strong acid or a strong base might, but they partially react to give you an equilibrium situation, and that equilibrium can be described by an equilibrium constant, which for the acids is going to be a Ka, and for the bases will be a Kb, right? And so we got to this example here of ammonia, which is a weak base. Ammonia reacts with water to give ammonium ions and hydroxide ions, and that would be the Kb for that. And because these Kb's and Kas are constants, they're numbers, you can look them up in a book. And so this is what you would find if you looked up the Kb for ammonia. It's kind of easy for people like me who have to remember these numbers to teach, because the Kb for ammonia actually has the same value as the Ka for acetic acid. The two most common weak acids and weak bases we use have the same numbers. That makes it nice and easy. But obviously you don't need to know these. We would always give you these numbers because they're constants. Yeah? Now another feature of this reaction is that, as we saw right back at the start, if we had acetic acid here, CH3COOH, then when it reacts with water, the acetic acid is the acid and it donates a proton to the water molecule. So the water molecule is the base in that reaction. Here it's the opposite. Here the ammonia is the base and the water is the acid. So the water is the thing that's giving a proton to the ammonia molecule, and you get hydroxide ions left over after the water's been an acid. So water can be an acid sometimes and it can be a base sometimes as well. And not only can it do that in the presence of another weak acid or a weak base molecule, but in fact it does it all the time just with itself. Right? So you can write an equation that looks like this, where you have two water molecules and one of which donates a proton to the other one. And so one of the water molecules can be an acid and the other one can be a base, and so we write an equation that looks like this. Two H2Os gives an H3O plus and an OH minus. And so here the water is being both an acid and a base at the same time. And this is given a fancy name, which is one of these things they like to make you remember at school because they think it's important, but it's not. It's called an autoprotolysis reaction. But I so don't care if you don't remember that word. But you should remember the equation, yeah? And it's an equilibrium. Obviously, this doesn't completely happen. Obviously, if you have a glass of drinking water, it doesn't spontaneously turn into a strong acid or something and dissolve you when you drink it. It only happens a little bit. It's an equilibrium. And that equilibrium constant expression looks like the one down the bottom. It's a bit like a KSP in that you don't put in any terms for the reactants, because here the reactants are liquid water. You don't put liquid water in. And so the K, which in this case is called Kw, W for water obviously, Kw is just the concentration of the H3O plus at equilibrium times the concentration of the hydroxide ions at equilibrium, and the value for that K is 1 times 10 to the negative 14. So it's a little number. But this equilibrium is an important one because it's always kind of going on in the background whenever you've got a solution of an acid or a base, right? Most of the time it's not important. Because, see, these numbers imply that these concentrations of H3O plus and OH minus that you have from this reaction are very, very small. And so if you add, say, some HCl or you add some acetic acid to some water, then the vast majority of the H3O plus ions are going to come from that acid molecule that you've added. But this is always going on in the background. And one of the consequences of that is that it means that there's always a relationship between the concentration of H3O plus and the concentration of OH minus in any aqueous solution that you've got. Right? Because regardless of what the H3O plus concentration is, whether it's little because it's just come from water, or whether it's much bigger because you've added an acid molecule to your water, the concentration of hydroxide ions is going to be related to that concentration of H3O plus ions through that Kw expression. Right? The concentration of H3O plus, whatever it is, times the concentration of hydroxide ions will always equal 1 times 10 to the negative 14. So that means if you know the concentration of H3O plus, you can work out the concentration of OH minus. And it follows from that that if you know the pH, you can work out the pOH and backwards, because remember pH and pOH are just mathematical manipulations of those concentrations. They're just another way of saying the same thing. And so we can write an expression like this, which we've seen that the Kw is equal to the concentration of H3O plus at equilibrium times the concentration of OH minus at equilibrium, which equals 1 times 10 to the negative 14. We can equally write this, that the pKw, the negative log of the Kw, is just going to be the negative log of the concentration of H3O plus the negative log of the concentration of the OH minus, and that's just the pH plus the pOH. So the pKw equals the pH plus the pOH, and that will equal 14, the negative log of 1 times 10 to the negative 14, right? So all we've done to go from the first line to that second line is just take the negative log of all the different things. Now you have to be happy that in the first line it's the concentrations multiplied by each other, and in the second line it's the pH plus the pOH. That's just math, right? You just have to kind of remember that that's the way it is. Unless you know log algebra. Heaven help us. So in neutral water, so-called, which isn't either acidic or basic, so that means that the concentration of the hydronium ions is equal to the concentration of the hydroxide ions, then the pKw means that the value of the pKw means that those concentrations of the hydronium and the OH minus must each be 1 times 10 to the negative 7 moles per litre. Right? So in neutral water, the concentrations of each of those ions is 1 times 10 to the negative 7, and so the pH will be 7. Now, it's probably a good time to point out that the pH is always referring to the concentration of H3O plus, right? Never the concentration of OH minus. Actually, it's probably not a good time to point that out. I will come back to that, but that's something that does catch people. If the concentration of H3O plus is greater than this, it's a bigger number than 1 times 10 to the negative 7, that means that there's more H3O plus than there is OH minus in your solution, and so you would say that the solution is acidic. And if you work through the numbers, that means that the pH will be less than 7. And conversely, if the concentration of H3O plus is less than 1 times 10 to the negative 7, that means that there's going to be more hydroxide ions than there is H3O plus. And so you would say that the solution is basic and the pH of the solution is bigger than 7. Okay? So this is nominally stuff that you've come across, this idea that an acidic solution has a pH of less than 7. But what I'm trying to do is relate it back to the Kw and the numbers. Yeah? Right then, so now, how do we work out the pH of a solution of a weak acid? Earlier we saw that if we said what is the pH of 0.1 moles per litre hydrochloric acid, then you go, oh, hydrochloric acid is a strong acid. I know this because I'm not given a pKa value for it, or I just remembered. So working out the pH is nice and straightforward. Working out the pH of a solution of a weak acid on the surface is the same, because the pH is just the negative log of the concentration of the hydronium ions. The trick here is that you've got to work out what the concentration of the hydronium ions is. And that's a bit more work, because it's an equilibrium situation rather than a reaction that goes to completion. So, imagine we said, what is the pH of a 0.024 moles per litre solution of ethanoic acid, of acetic acid? And so the steps. And the first step is this. We write the equation, right? Write out the chemical equation for the reaction that happens, and we write out the equilibrium constant expression for it. Okay, so maybe I'll give you 30 seconds to have a go at that. So you want to write the chemical equation corresponding to acetic acid being an acid, reacting with water, donating its proton to give products, and then write the equilibrium constant expression that goes with that. Okay, so here's the equation. So ethanoic acid is CH3COOH plus water, and that forms an equilibrium with CH3COO minus, the acetate or the ethanoate ion, and H3O plus. And so the Ka for that will be the concentration of CH3COO minus at equilibrium, little e, times the concentration of the H3O plus ions at equilibrium, divided by the concentration of the unreacted acetic acid at equilibrium. And all of that equals a number. That ratio of those concentrations equals a number, and the number is 1.74 times 10 to the negative 5. Yep?
How did we know it was that number?
Because we would have told you. Or we'd have given you that the pKa was 4.76, and then you would have to convert that to a Ka. Yeah? Okay. So that's that. So this is what you should always do first off, right? And this is not only because the marker will like to see that this is your thinking, but because it's important for your thinking. Because this is where people get horribly confused, right? And if you can, and there'll be people out there going, yeah, I know how to do this, but tomorrow when we do buffers, I will guarantee that you will immediately get confused when the heat is on, and you'll start doing buffer calculations rather than doing this, and vice versa. I see this all the time, right? So write out all the steps, make it nice and clear in your own head what you're about and what you're doing. Yeah? And then it says at the bottom, remember that the pH is the negative log of the concentration of H3O plus. So what we need to do is we need to work out what this is, right? So what we're going to be about, this gives us a number, and it says that the concentration of this times the concentration of this over the concentration of this equals that number. What we want to do is we want to work out what that number is, because it's that which we need to then work out the pH, which is what the question's asking us to do. Right? So somehow we need to work out what this is, and what this is, and what this is. We know that the ratio of these concentrations equals that. We need to work out what this number is. Okay? And so, step 2, the assumptions. And this is something which, if you haven't come across it already, you're going to come across quite a lot, and I would suggest lots of first-year papers. Because what we do is we say, well, you can do this exactly, but you can't do it exactly in your head. You can do just about any math exactly on a computer with the appropriate software now, and this is no exception. You can do this calculation properly. But what we do in first year is we teach you a way of getting the answer almost correct by making some assumptions. And so on the one hand, this is kind of fudging the answer because it's just easier, but on the other hand, it's testing that you understand the underlying chemistry that's going on to appreciate that what we're about to do is reasonable, right? So there's benefit to this, even if it is just a way to get you a quick and dirty answer rather than an exact answer. So, what do? In order to solve the Ka expression, we need to make two assumptions. The first one is that we assume that the concentration of H3O plus at equilibrium equals the concentration of CH3COO minus at equilibrium. We assume that those two values are the same. And you could say, well, that seems completely reasonable, because if I look at my chemical equation that I've just written down, it says CH3COOH plus water gives CH3COO minus plus H3O plus. It's a 1 to 1 to 1 to 1 balancing. So every time I make one lot of acetate, I make one lot of H3O plus. So their concentration should be the same. Yeah? Of course, what that's forgetting is that the water molecules are also making H3O plus from that autoprotolysis reaction. And so this is an assumption, but it's fair enough because the amount of H3O plus that's coming from that reaction of water reacting with itself will be very, very small compared to the numbers we're talking about here. And so it's going to be not exactly right, but it's going to be very close to being right. Yeah? So this is an assumption. Assuming that those are the same will not be exactly true. The concentration of H3O plus ions will be slightly bigger than the other, but not by enough that it matters. Right? So that's the first assumption. The second assumption is the one that maybe seems a little bit more strange. We assume that only a tiny amount of the acid actually dissociates. Right? The value for the Ka is 1.74 times 10 to the negative 5. That's a little number, and so that tells us that the reaction doesn't go very far before it reaches equilibrium. What we're going to do is this. We're going to assume that because only a tiny amount of the acetic acid actually dissociates and reacts with the water, we're going to assume that none of it does. Right? Hello?
What if the Ka was actually reasonably low?
Then we are not going to ask you about that sort of acid this year. Yep. I mean, you're exactly right. But then you would need a computer to do it properly. Or at least more math than I have. But we're just going to stick with the ones for which this applies. Yeah. So, this means that we can make this approximation. We assume that the concentration of the acetic acid at equilibrium equals the concentration of acetic acid initially. So that over there's got a little I on it, yeah? So a little I there for initial. And this is where I really like having the little E's here, because when you write your nice working here for this, you can at this step go concentration of CH3COOH brackets E equals concentration of CH3COOH brackets I for initial. That's nice and clear and succinct, but it's saying this is the assumption I'm making here. So what we're doing is that we are assuming that none of the acid reacts with the water in order to work out how much of the acid reacts with the water. Yeah? So it seems a little bit hairy. My wife, who did philosophy, would probably not approve about this argument. But it, again, is going to give you a number which is not exactly right, but is going to be so close to being right that it doesn't matter for our purposes. Right? And of course, this helps us because this number here, the concentration of CH3COOH initially, is the number we're given in the question. Right? We tell you this, it's the 0.024 moles per litre. And so now we're making some progress. Because here's our Ka expression that we start off with. Ka is the concentration of CH3COO minus at equilibrium times the concentration of H3O plus at equilibrium divided by the concentration of CH3COOH at equilibrium, and all of that equals 1.74 times 10 to the negative 5. What we can do is we can use assumption 1 and rewrite that Ka expression to look like this. We can now on the top put concentration of H3O plus at equilibrium squared. Right? Because if both of those concentrations are the same, whatever number they are is the same number, then multiplying the number by itself is the same as having that number squared. And so we rewrite the top line like that by assumption 1. And see, I would do it this way if I was doing my working. Right? I would assume that the marker knows the assumptions as well, and so you can say assumption 1 and then just change that top line for H3O plus squared. Yeah? We could just as easily have written the top line of that as concentration of CH3COO minus squared. Right? That still mathematically would be correct, but remember the point is to work out the H3O plus concentration because that's what we need to work out the pH. We happy so far? Right, so that's assumption 1. And then assumption 2 means that we can write this. Now on the bottom, we can write the concentration of CH3COOH initially. And so what we've done now then is we've gone from the Ka expression at the top, where we didn't know this, and we didn't know this, and we didn't know this, we didn't know any of those concentrations, to a situation down here now where we know what this is, and we don't know what that is, but we do know what this is. So now we only have one unknown. And so we can work out what the value of this unknown is, because we know everything else. Yeah? So those assumptions have enabled us to simplify the calculation. And so, here it is again. And so step 3 is solve for the concentration of H3O+. And so now we just stick in the number on the bottom. So it's going to be the concentration of H3O+ squared divided by 0.024 equals 1.74 times 10 to the negative 5. And then we can rearrange that. Oh, I was going to get you that book. Sorry, just remembered. And we get this by multiplying both sides by the thing on the bottom. And then the concentration of the H3O+ itself will just be the square root of all of that. And so you can work out that the concentration of H3O+ is 6.46 times 10 to the negative 4 moles per litre. Right? If it had been 0.024 moles per litre hydrochloric acid that we started with, then the concentration of H3O+ would have been 0.024 moles per litre. Yeah? This number here is about 100 times smaller. And so that shows you the difference between a strong acid and a weak acid. All right? The amount of H3O+ you get from the same concentration of acid is a 100th as much, because only about 1% of all the molecules actually react with the water. Okay? Are we happy with this? Right? There'll be some of these to do in the tutorial. This, now, I'm pretty sure the next slide says, oh, sorry, we're not finished. There you go. There's a mistake that people make as well. I almost made it myself. The question did not say what is the concentration of H3O+, it said what's the pH. So you have to do that bit as well in the end. Okay, and so the thing of it is that not only is this in level 3, and it's undoubtedly something that they ask you, and they probably want you to do it in exactly this horribly prescribed way, but it is something that you will get marks for being able to do in 191. Guaranteed, it's always there. Just like that enthalpy stuff, it's always there. And sometimes it will be in the final exam, which is cool, because then you get marks for working, and it might be worth 2 or 3. And sometimes it's in the mid-semester exam, which is multi-choice, and so you only get 1. Right? And we don't care about the working. But either way, you need to be able to do these calculations. We can do a similar sort of calculation to work out the pH of a solution of a weak base. This is a little bit harder, but only because there's a couple of extra steps in there. But this, you should again write out all the steps the same way. Right? So, if the question is what's the pH of 0.15 moles per litre ammonia solution, then the steps are the same. Step 1, write out the balanced chemical equation that describes the equilibrium, and write the Kb as it will be this time. Second step is to make the assumptions, and so take that Kb expression and then modify it using those assumptions. And then the third step is solve that new Kb expression to work out the concentration, in this case, of the hydroxide ions. And then you, from that, work out the concentration of H3O+. Yeah? So the strategy is to work through the calculation just as we've done, but to find the concentration of OH-. Because remember, the Kb expression will have OH- on the top line, not H3O+, because it's a base. But that doesn't matter. The assumptions still work. The way that you change the Kb expression is the same as you would for the Ka. But then when you get to the end, you'll work out the concentration of hydroxide ions, and then you can work out the POH. And then once you've got the POH, you can use that expression that we saw before, that the POH plus the pH equals 14, and you can convert the POH to a pH like that. Yeah? So that's where you would start. And remember, we would give you the value of the KB or the PKB as a part of the question. Right. And so the pH of that solution is 11.2. Right, so there's some homework or some extra thing to do in the tutorial. You can work through that one and see if you can't get 11.2 as the pH.